In this video, we solve problem 6.4.8 from Nagle's Fundamentals of Differential Equations, 7th edition. We're asked to find a general solution to the Cauchy-Euler equation. See, it's third order, and it's non-homogeneous. We're told that x is greater than 0. And we're given a fundamental set of solutions. X is a solution to this equation, or the corresponding homogeneous equation, 8 times x times natural log of x is a solution to this equation, and x to the fourth is a solution to this equation, modified where the right-hand side is 0. All of these guys will work, will satisfy this when the right-hand side is 0. Well, that's enough to get us a y sub c. Since it's a third order equation, we have 3 linearly independent solutions to this corresponding homogeneous equation. Most of the time we would have to find those linearly independent solutions ourselves, but this time they were given to us. Now, y sub c will be c1y1 plus c2y2 plus c3y3. But remember, c1, c2, and c3 are constants. So we could use the y1, y2, and y3 that they gave us. We could use c1x plus c2 times 8x natural log of x plus c3 times x to the fourth. We could do that, but we really don't need this 8, because if 8x times natural log of x is a solution to this equation, so is x natural log of x. A constant times 8 is just a different constant. So if you want, you can use x natural log of x for your y2 rather than 8x natural log of x. It's probably a good idea to do that. It would simplify your calculations. But you can use the y2 that they gave you, and the 8s will cancel out, as we'll discuss. The benefit of getting rid of the 8 is that it will make the numbers, the actual arithmetic that you're doing as you're doing these calculations, easier. You'll just be working with smaller numbers, not multiples of 8 times different expressions. But because most of the students in my class decided to use the y2 as given, I'm going to go through this method using y2 as given. So we know that these are 3 linearly independent solutions to this third order equation. So y sub c is this. And then if we want to solve the non-homogeneous problem, where the right-hand side is x squared, we're going to let y sub p equal u1 y1 plus u2 y2 plus u3 y3, where those 3 functions, u1, u2, and u3, are not constants. Then by variation of parameters, the derivation that we did in class or in the videos, u1 prime, u2 prime, and u3 prime are given by these expressions. Where w is the Wronskian of our 3 linearly independent solutions, and w1, w2, and w3 are related to the Wronskian, but we replace one of the columns with 0, 0, and a function we'll call f of x, which we will identify later. So we're going to say that u1 prime, u2 prime, and u3 prime satisfy this, or these equations, where w is the Wronskian. So remember, the Wronskian is a 3×3 determinant. So in the first column, we'll have our first solution x. Its first derivative is 1, and the derivative of 1 is 0. So just take derivatives until we have 3 rows there. And then for the second one, we have 8x times natural log of x. Now, when I take the derivative of this, it takes a little bit more work. We have to use the product rule. We'll have the derivative of the first, which is 8, times the second, which is natural log of x, plus the derivative of the second, which is 1 over x, times the first. 1 over x times 8x is just going to give us an 8. The x's will reduce. And then when we take the derivative of this again, we get 8 times 1 over x, which is 8 divided by x. And the derivative of just the 8 by itself is 0. Okay, so that's our second column. And the third column, our third solution was x to the fourth. We take its derivative, bring the power down, multiply by x to the 1 less power. Then here we're going to bring the power down again. 4 times 3 is 12. Multiply by x to the 1 less power. And we'll have that right there. Now, whenever you evaluate a determinant, you have a choice. You can multiply, or you can expand, along any row or column that you like. Any one of those is fine. To simplify your calculations, it's helpful to use a row or a column that contains a 0. Since this column contains a 0, I'm going to expand along this row. There is a sign convention though. You always start in that first row, first column entry with a positive sign, and then you alternate signs as you're going across your rows in the matrix. So I have plus, minus, plus, and then you always pick up where you left off. So since there's a plus here, we'll have a minus, plus, minus, pick up where you left off, plus, minus, plus. And then you ignore these signs over here. The signs that we're really interested in are these plus, minus, plus. And you're taking each of these factors here. You're multiplying by a positive 1, a negative 1, and a positive 1. And then you're also multiplying by the 2 by 2 determinant that comes from crossing out the row and column containing that entry. So we've got positive x times the 2 by 2 determinant that comes from crossing out the row and the column containing x. So we have 8 natural log of x plus 8. We have 8 over x here. And we have 4x cubed here and 12x squared. And we'll evaluate that in a little bit. And then we'll have minus 1 times, cross out the row and column containing that negative 1. We've got an 8x natural log of x and an x to the fourth in that first row, and then we'll have an 8 over x and a 12x squared. And then on the last one, we're adding 0 times, cross out that row and that column, a 2 by 2 determinant. It doesn't really matter what it is because we're multiplying it by 0, so the product will be 0. Okay, so that's our Wronskian. Now we just need to evaluate this. So I have x times. Now I have this quantity times this. So I can think of that as a binomial times that. I know it's not technically a binomial because it's not a polynomial, but we're thinking of that as two separate terms. Each of those, or we can distribute this 12x squared to each of the terms. And so this is what we get. 12 times 8 is 96. And then we'll have an x squared there times natural log of x plus 96 x squared. And then you're going to multiply across this diagonal. 8 times 4 is 32. And you've got an x cubed there and an x in the denominator, so one of those will reduce, so you'll get a 32x squared. And you're multiplying across this diagonal and then this one as well, and then you're subtracting. And of course, we have like terms there. 96 minus 32 is 64. Okay, now notice that we had an extra factor of 8 here and an extra factor of 8 here, which made the numbers larger, that we wouldn't have if we had made y2 just x natural log of x instead of the 8 natural log of x. It's okay, it just makes the arithmetic a little bit more challenging if we're doing it in our heads. Here we have same thing, you've got -1 times this determinant, you're multiplying here and then there, and then you're subtracting. We're gonna have a 96 x cubed this time times natural log of x minus 8. And we've got x to the fourth in the numerator and an x in the denominator, so one of those will reduce. If you distribute, so now we have this. Now if we distribute the x here, we get this. And if we distribute the -1 over here, we get that. And notice that these two terms reduce, and we have 64x cubed and an 8x cubed. So that's going to give us 72x cubed for our Wronskian. That's W. Now let's do it again. W1 looks just like the Wronskian, but you replace the first column with 0, 0, and f of x, where f of x is closely related to this right-hand side. F of x is the function that you have on the right-hand side when the leading coefficient is 1. So we need to have a 1 in front of the y triple prime, which means we divide every term by x cubed, which is the same as just dividing both sides of the differential equation by x cubed. And then on the right-hand side, we have this, and that is our f of x. And of course, f, or x squared over x cubed, simplifies to 1 over x. We just end up with 1x left in the denominator. So that's our W. W1 will look very similar. But we replace the first column with 0, 0, and f of x. So we have 0, 0, and 1 over x now, and the other two columns are exactly the same as they were before. Now we can expand along any row or column we want. We want to use the one with all the zeros. So we'll do this. And again, the sign convention is plus, minus, plus, minus, plus, minus, plus, minus, plus. So we will have 0 times a 2 by 2. Minus 0 times the determinant of a 2 by 2. Plus 1 over x times the determinant of the 2 by 2 that results from crossing out the row and the column containing the 1 over x. So we'll have 8x natural log of x, 8 natural log of x plus 8. And then these two entries from right there. And of course, anything times 0 is 0, so these guys are gone. And you end up with this. Now, I want to distribute. I want to multiply across this diagonal and subtract. This times this will give me a 32. X times x cubed is x to the 4th times natural log of x. And then over here, we want to distribute the x to the 4th, but we also want to distribute the negative. So I'm thinking of taking each term here and multiplying by a negative x to the 4th. So I'll have negative 8 x to the 4th natural log of x minus 8 x to the 4th. I'm taking that and distributing there. And then, of course, we've got 32 of these, and we're subtracting 8 of them, so that means we have 24 of them. And we are dividing that by x. So the powers of x will go down by 1. And if you want, you can factor out an 8x cubed. And that's what we get. Now notice that that has a factor of 8 in it. It came from the fact that this column was multiplied by an 8. If the 8 was left off of our y2, we wouldn't have an 8x cubed here. And notice that this is 72x cubed. Without this 8, it would have been 9x cubed. So multiplying the whole row by an 8 actually made the determinant 8 times as large. And that's okay, it's all going to cancel out, and we're still going to get the right answer. So that's our W1. W2 is very similar, but we leave the first column alone and the third column alone. And this time we replace the second column with 0, 0, and f of x. Now this time we don't have an extra factor of 8 here, but it'll work out, and we'll talk about why in just a bit. Here we've got an x, a 1, and a 0. We have a 0, and f of x was 1 over x. And then we've got this. Wow, we have lots of options for rows or columns to expand along. But we want to use the one with the most zeros, so we're going to use this one. Now, sign convention is you start with plus, minus, plus, minus, plus, minus, plus, minus, plus. So when we expand along this column, we end up with 0 times a 2 by 2 determinant, which is 0, plus 0 times a different 2 by 2 determinant, which is 0, minus 1 over x, times the 2 by 2 determinant that comes from crossing out this row in this column. So you have a 1 and an x and a 1 and an x to the 4th and a 4x cubed. This times this gives me 4x to the 4th, and we're subtracting x to the 4th. So that's going to give me a negative 1 times 3x to the 4th all over x, and that'll be negative 3x cubed. Again, that one did not have a factor of 8 because we replaced the second column with the 0, 0, and f of x. Last one, 0, 0, f of x. Oops, sorry. For W3, making a mess here. We replace the third column with 0, 0, and f of x. I don't know why I started replacing the first column with that. Okay. So we have the x, the 1, and the 0. We have the 8x natural log of x, the 8 natural log of x plus 8, and the 8 over x, and the 0, 0, and 1 over x. Expand along the row or column that's easiest. We're going to use this one again. Sign convention plus, minus, plus, minus, plus, minus, plus, minus, plus. So we'll have 0 times a 2 by 2 determinant plus, or minus 0 times a different 2 by 2 determinant plus 1 over x times the 2 by 2 that comes from, or the determinant of the 2 by 2 that comes from crossing out this row in this column. So we've got an x and a 1 and 8x natural log of x and 8 natural log of x plus 8. This times this. Distribute the x to both terms. Then we're subtracting that times that. That's nice. These guys reduce. We have 8x divided by x, which is just 8. And that's 8 times larger because of that extra factor of 8 in that middle column. So W3 would have been a 1 without the extra factor of 8. Okay, so we've computed our W1, W2, and W3. Now we want to put those pieces together to come up with U1 prime, U2 prime, and U3 prime, and then we want to anti-differentiate. So we have U1 prime is W1 divided by W. And W1 turned out to be 8x cubed times 3 natural log of x minus 1, all divided by W, which ended up being 72x cubed. The x cubes reduce, and 8 goes into 72 9 times. So we end up with a 1/9 times 3 natural log of x minus 1. We need to anti-differentiate that to get U1. If you want, you can distribute the 1/9. It's up to you. 1/9 times 3 is going to give me a 1/3. And we can handle this and this separately. So I'll factor out the 1/3 of that integral. Then I have a negative 1/9 times the integral of 1. Now for this one, the answer is not 1 over x. A lot of students want to say the answer is 1 over x there, but that's actually the derivative of natural log of x, not the antiderivative. For an integral that looks like this, we have to use integration by parts, where u is natural log of x and dv is dx. Of course, this is not any of the u's that we're talking about in the context of our problem. This is just for integration by parts. Oops, that should be a dx. So we compute du, that's 1 over x dx, derivative, not antiderivative. And then we have v, that's the antiderivative of 1, which is just x. According to integration by parts, we get uv minus the integral of v du. So I have 1/3 times u times v, so that's going to be an x natural log of x, minus the integral of v times du. Now, a lot of students make the mistake of just taking the antiderivative of that and the antiderivative of that and multiplying them. They get x squared over 2 times natural log of the absolute value of x. Don't do it. You have to simplify this first. We don't have a product rule for antiderivatives. I mean, the closest thing that we have is this integration by parts formula, which came from the product rule. But we can't just take the integral of this part and multiply them together. We have to reduce instead. We can think of that as an x over 1, and that is an x in the denominator. So those x's will reduce, and we just end up with a 1. The antiderivative of 1 is, of course, just x. So we have 1/3 times natural log of x, or x natural log of x minus the antiderivative of 1, which is x, plus a constant. We'll save the constant for the second integral. The integral of 1 with respect to x is just x. So we'll have negative 1/9 x plus some constant. So I have that there. Let's choose the constant to be 0 because we're going to multiply u1 by y1, and we don't need a constant times y1 as a part of our y sub p. Now, if you want to simplify, and you probably do, I'm going to distribute that 1/3. And these guys are like terms. So I need a common denominator here. The LCD of 3 and 9 is just 9, so I'll multiply this fraction by 3 over 3 in order to make that denominator a 9. So what we end up with is this, 3 over 9, or negative 3 over 9 minus 1 over 9. It's going to be negative 4 over 9 times x for our u1. Okay, now let's compute u2 prime. And then we'll use that to compute u2, the antiderivative of that. W2 is this guy, negative 3x cubed. And w was 72x cubed. So we can simplify that. 72 is 9 times 8, so that's 3 times 3 times 8. The 3's reduce, the x cubes reduce, and we end up with a negative 1 over 24. So the u2 is the antiderivative of negative 1 over 24, which is that times x, plus a constant, and we're going to choose that constant to be 0. Okay. And u3 prime is w3 over w, and w3, let's see what that was, turned out to be 8. These are really simple. We're dividing by 72 over, or 72 times x cubed. Of course, 8 goes into 72 9 times, and we end up with 1/9. And if you want, you can call that x to the negative 3. So u3 is the antiderivative of this. You'll want to bring the 1/9 down, add 1 to the exponent, and then divide by the new exponent. Add your constant of integration. And we'll choose for that constant to be 0. So we have negative 1 over 18, and that's a 1 over x squared, so we'll end up with an x squared in the denominator after we simplify. Okay, now we've been talking about the fact that there was an extra 8 and everything. I would like to relate that back to y sub p now. So remember, y sub p is u1 y1 plus u2 y2 plus u3 y3. And u1 came from taking w1 and dividing it by w. Now w1 and w both had the same second column, like this. So this had an extra factor of 8. This had an extra factor of 8. So the 8's cancel, and we ended up with this expression. So you get exactly the same u1 prime using with this column as you would have otherwise. It's just when we did the arithmetic, we ended up with this extra 8 and the 72 instead of just a 1 and a 9. But we end up in the same place because the 8's reduce, and we get this. So u1 is exactly the same, and then we multiply by y1. And u1 turned out to be 1/3 x natural log of x minus 4/9 of x. And we're multiplying it by y1, which was x. And we'll distribute in a moment. Now u2 is a little different. u2 came from w2 over w. And remember, w had an extra factor of 8 because of that 8 in that second column. But w2 didn't. W2 came from a determinant that looks like this. We replaced the second column with 0, 0, and f of x. So the extra factor of 8 is gone because of that replacement. So this u2 that we found, this negative 1 over 24 times x, is different than the u2 you would have found if that 8 was missing. But what I want you to see is that you've got an extra factor of 8 in the denominator, so that's a 1/8 that is multiplying this. So we're going to take this, which is 1/8 of negative 1/3 x, and then we're going to multiply it by y2, which was 8x natural log of x. Do you see how the 8 from the w cancels with the 8 from the y2? So you end up with negative 1/3 x times x natural log of x anyway. You end up in the same place. So that's the point. And then for u3, we have this function. And we're multiplying it by y3, which is x to the 4th. Now we'll do a little bit of distribution, simplification, and see what we get. We have 1/3 x squared natural log of x minus 4/9 x squared. Here we have a negative 1/3 x squared natural log of x. Here, 2 of those x's will reduce. We still have an x squared in the numerator, so we have negative 1/18 of x squared. And notice what happens. These two terms are identical but with opposite signs, so they reduce. Now in this one, we need a common denominator. I've got an x squared term here and an x squared term here. This one has a denominator of 9, that one has a denominator of 18. In order to make this an 18, I need to multiply by 2. That's fine, but I have to multiply the numerator by 2 as well, so I don't change the value of the fraction. So what I end up with is 9 times 2 is 18. Negative 4 times 2 is negative 8. So I have negative 8 over 18, which is the same as negative 4 over 9. Negative 8 over 18 minus 1 over 18 is negative 9 over 18. And negative 9 over 18 is the same as negative 1/2. So y sub p turns out to be negative 1/2 x squared. And that's very nice. That means we're almost done. So we found u sub 3 prime, and then we computed u sub 3. And then we found the form of y sub p. And the last thing that we need to do is state the general solution. General solution is y equals y sub c plus y sub p. That's c1 y1 plus c2 y2 plus c3 y3 plus y sub p, which is negative 1/2 of x squared. Now you don't have to include that 8 there. This is on the interval from 0 to infinity. They told us that x was greater than 0 at the very beginning. You don't have to have that 8 there because a constant times 8 is just a different constant. But if you want to, you can have the 8 there. And if you chose to not use the 8 in your y2, again, all the calculations would have been a little simpler, and we would have ended up with the same general solution. Careful with the arithmetic. I've seen a lot of students that made a mistake with the arithmetic at the end here, just adding or subtracting those fractions. When in doubt, if you want, you can use your scientific calculator to do your arithmetic. But remember, whatever we do to the denominator, we have to do to the numerator. So this is not negative 5 over 18. It's going to be negative 9 over 18, which gives us the negative 1/2.